Hi everybody, Seth McGowan here from the Adirondack Sky Center and Observatory in Tupper Lake, New York. Today I'm going to talk about the basics of how telescope lenses and mirrors get light to your eyes so that you can see objects from far away through the eyepiece. This is not going to be advanced physics or anything, just a basic introduction to light collection. There are two ways that telescopes collect light and deliver or concentrate it for you. Those two ways are either by refraction or reflection. You've all seen mirrors or other reflective surfaces that mirror back what's in front of them. So try to guess the kind of telescope that collects light through the same process of reflection. You got it. Those are called reflector telescopes, but we'll get back to those in just a minute. Let's start with refractors. Believe it or not, you're probably familiar already with the principle of refraction. If you've ever looked at a straw in a clear glass of water and noticed that it appears to be bent, then you've experienced refraction already. Refraction occurs when light passes through one material to another of different density. When that happens, the light bends at an angle, and there's a very specific formula used that can calculate what that angle will be. So let's look back at the glass of water and straw. As the light passes from the air to the water, or water to the air, it becomes redirected or refracted. As your eye sees it, the top of the straw is not refracted because it's not passing through a different material. But the bottom of the straw, the part below the water, has passed between the air and the water and has become redirected or refracted. Your eye sees the top in its original position and the bottom in its new position, appearing to be bent. The refraction effect is magnified when the second material is curved. Luckily, telescope makers know how to use that formula to make glass lenses that bend or refract light to become redirected at a specific point called the focal point. So let's see how that works inside of a telescope. You've seen a common refractor telescope for sure. They have long optical tubes with lenses inside of them that bend the light at a specific angle and focus that light to the eyepiece where you look. The distance between the lens and the focal point is called the focal length. In the case of a refractor, the focal length is determined in a straight line from the lens to the eyepiece. Reflector telescopes, as we said a few minutes ago, use mirrors to reflect and concentrate the light to that specific point, still called the focal point. As with refractors, many of you have already seen how reflection works in everyday objects. If you've ever seen a two-sided mirror, for example, where one side is flat and the other side is curved inward, then you've seen the basics of how a reflector telescope works. The flat side shows the reflected image at normal size. The curved side magnifies the reflected image. The mirror inside a reflector telescopes are curved inward, so the light that comes in is reflected back on an angle from the point of the mirror that it hits. And these points are all different across the entire surface of the mirror, but they all have one very important thing in common. They all direct light to a single point. And you guessed it, that point is called the focal point. And it doesn't stop there. After the light is reflected off of the primary mirror, it's then reflected a second time by a flat mirror on a 45-degree angle and out the side of the telescope into the eyepiece where you can see the object. This type of telescope is commonly referred to as a Newtonian telescope. A more specific type of reflector telescope that uses two curved mirrors that direct light is called a Schmidt-Cassegrain. The primary mirror reflects light onto a secondary mirror, then out through the back of the telescope where the eyepiece is located. I want to show you again that the focal length of a reflector telescope is folded a few times due to all of this reflecting, so they may look shorter than a refractor, but have the exact same focal length. One final important note when it comes to brightness: bigger is better. That's to say that a 14-inch reflecting mirror has more surface area than a 10-inch reflecting mirror. That extra surface area collects more light, but concentrates it into the same eyepiece, making the object in a 14-inch reflector appear brighter than in a 10-inch. Think of it like two different sized umbrellas upside down in the rain. If the rain droplets symbolize light, then a bigger umbrella will have more water in it than the smaller one. More light equals brighter objects. It's not really that simple, but the idea is sound. And of course, the same is true with refractor telescopes. More light collection is always better for viewing. On a side note, since we're talking about brightness, I'm sure you know never to point the telescope directly at the sun without very specific filters for that purpose. Well, I hope this has helped you understand the very basic principles of how telescopes collect and concentrate light from distant objects to your eyes. This is Seth McGowan for the Adirondack Sky Center and Observatory, signing off and wishing you happy stargazing.